The universe has long captivated humanity with its immense scales of distance and time, drawing our gaze upward and outward in wonder and contemplation. How far does it stretch into the darkness? Where does it end, and what mysterious realms lie beyond the star fields and the streams of galaxies that extend as far as our most powerful telescopes can see? These profound questions are beginning to yield answers through a series of extraordinary new lines of investigation and revolutionary technologies that are letting us peer not only into the most distant realms of the cosmos, but also into the behavior of matter and energy on the smallest of scales. Remarkably, our growing understanding of this kingdom of the ultra-tiny, deep inside the nuclei of atoms, is now enabling us to glimpse the answer to one of humanity's most ancient questions. How large is the universe? Asterisk in ancient times. Most observers gazed upon the stars as a celestial sphere surrounding Earth, a divine canopy and the dwelling place of deities who controlled human fate. The Greeks were the first civilization to fundamentally shift this perspective, seeing celestial events as natural phenomena subject to human investigation and rational inquiry rather than the fickle whims of capricious gods. One philosopher and dedicated skywatcher named Anaxagoras proposed a revolutionary idea for his time, that meteors are made of materials found on Earth and therefore might have even originated from our own planet. This was a radical departure from supernatural explanations, suggesting that the heavens and Earth shared a common nature. Those early astronomers and philosophers built the intellectual foundations of modern science, establishing principles of observation, measurement, and logical reasoning that would guide inquiry for millennia to come. But they would be utterly shocked and amazed to see the discoveries being made by their scientific counterparts today, revelations that have transformed our understanding of existence itself. Asterisk. The stars and planets that once harbored the gods are now understood as infinitesimal, parts of a vast scaffolding of matter and energy that extends far out into space, forming structures of breathtaking complexity and scale. Just how far this cosmic architecture extends began to emerge in the early 20th century, during a revolutionary period in astronomy. Working at the massive new 100-inch Hooker telescope perched on California's Mount Wilson, astronomer Edwin Hubble, along with his dedicated assistant Milton Humason, carefully analyzed the light emanating from fuzzy patches of sky known then simply as nebulae. Through painstaking observation and measurement, they demonstrated conclusively that these were actually distant galaxies located far beyond the boundaries of our own Milky Way, island universes in their own right containing billions of stars. Asterisk. Hubble and Humason made an even more startling discovery that would reshape cosmology forever. They found that most of these galaxies are moving away from us, receding into the cosmic distance. Even more remarkably, the farther out they looked into space, the faster these distant objects were receding from our vantage point. This fundamental relationship, now enshrined in physics as Hubble's law, carries a profound implication. It suggests that there must have been a time when the matter in all these galaxies was together in one place, compressed into an inconceivably dense state. Everything that astronomers observed through their increasingly powerful telescopes would have dated back to a singular beginning, an explosive genesis now called the Big Bang. This idea initially seemed so radical that many scientists resisted it, yet the evidence became overwhelming. Asterisk. That the universe could be expanding had actually been predicted back in 1917 by Albert Einstein through his revolutionary general theory of relativity, except that Einstein himself, initially, didn't believe his own equations. He was so convinced that the universe must be static and eternal that he added a mathematical term called the cosmological constant to his equations to prevent cosmic expansion. It wasn't until he examined Hubble and Humason's observational evidence firsthand that Einstein accepted the reality of an expanding universe, later calling his resistance to this idea his greatest blunder. Einstein's general theory of relativity suggested something even more profound and counterintuitive than mere motion through space. Galaxies could be moving apart because space itself is expanding stretching like the surface of it inflating. The Loon, asterisk, when a photon gets blasted out from a distant star, it embarks on a journey through a cosmic landscape that is continuously getting larger and larger, constantly increasing the distance it must travel to reach our telescopes here on Earth. The photon isn't just moving through space. The space through which it travels is itself expanding. This means that determining how large the cosmos has becomes, since the Big Bang depends on two crucial factors: how long it has been growing and the rate at which it has been expanding. Both of these values have been targets of intense scientific investigation. Recent precision measurements gathered by the Hubble Space Telescope and other sophisticated instruments, including observations of distant supernova and measurements of the cosmic microwave background radiation, have brought scientific consensus that the universe dates back approximately 13.7 billion years. In that immense span of time, a beam of light traveling at the cosmic speed limit would have covered 13.7 billion light years, or about 1.3 quadrillion kilometers. This almost incomprehensible distance represents the observable horizon under a simple calculation. However, taking into account the expansion of the universe itself during the light's journey, the most distant galaxies discovered by the Hubble Space Telescope and other instruments are actually located about 46 billion light-years away from us in each direction. This means the observable universe has a diameter of approximately 92 billion light-years, with the most distant visible objects almost 92 billion light-years from each other. Asterisk. So is that the ultimate size of the universe? According to a dramatic new theory that describes the origins of the cosmos, the answer is a resounding no. This theory holds that our 92 billion light-year patch is a mere speck, an almost infinitesimal fragment within the universe as a whole. The theory is based on remarkable discoveries about the fundamental nature of empty space and energy. Scientists have found that energy is constantly welling up from the vacuum of space itself in the form of virtual particles of opposite charge, matter and antimatter, that briefly flicker into existence before annihilating each other. This quantum foam, as it's sometimes called, suggests that nothingness isn't truly nothing at all. Asterisk back in the early 1980s. The physicist Alan Guth proposed a revolutionary modification to Big Bang theory called cosmic inflation. He suggested that energy fields embedded in the vacuum of space during the universe's first moments had suddenly tipped into a higher energy state, causing space and time to literally inflate at an exponential rate. According to this theory, the universe went from smaller than an atom to cosmological size within an almost incomprehensibly short time period, a tiny fraction of a second. The expansion was so rapid that it defies ordinary comprehension in far less than a blink of an eye. The cosmos grew by a factor larger than the number of atoms in the observable universe. Asterisk, as a result of this inflationary period, according to Guth's calculations and subsequent refinements by other physicists, the universe as a whole would have grown to approximately 10 billion trillion times the size of the observable universe. We can detect with our instruments. That's a 10 followed by 24 zeros, a number so vast it challenges human intuition. To put this another way, using a remarkable analogy, the whole universe is to the observable universe as the observable universe is to a single atom. We are living in a tiny observable bubble within an enormously larger cosmos that extends far beyond what we can ever hope to see. Asterisk. The incredible fury and rapid pace of cosmic inflation helps explain several puzzling features of our universe. It accounts for the immense size and remarkable smoothness of the cosmos on large scales. It explains why the universe appears essentially the same in all directions, despite regions being so far apart that light hasn't had time to travel between them since the Big Bang. But to truly succeed as a scientific theory, cosmic inflation must also account for how the universe produced what we see around us today. All those stars scattered across the night sky, the galaxies that group them into vast cities of light, the clusters and superclusters of galaxies that form the large-scale structure of the cosmos, and ultimately, the conditions that led to planets like Earth and to life itself. Scientists are now attempting to piece together the chain of events that launched our universe in its earliest moments by generating what you might call a little bang, recreating in miniature the conditions that existed a fraction of a second after the cosmic birth. At the Brookhaven National Laboratory in New York State, researchers are conducting extraordinary experiments using the relativistic heavy ion collider. They blast gold atoms in opposite directions down tunnels almost 2.5 miles long, in a vast circular track. When these atoms reach velocities just short of the speed of light, approaching this cosmic speed limit with astonishing precision, they are sent into violent collisions with tremendous energies. Asterisk, a fireball erupts from. These collisions reaching temperatures exceeding 2 trillion degrees Celsius, far hotter than the core of any star in the universe today. As far as we know, the last time anything in our universe reached temperatures this extreme was about a millionth of a second after its birth in the Big Bang. What interests the scientists studying these collisions is the splatter of subatomic particles that emerges, a super hot soup of quarks and gluons that fundamental theory says gave rise to matter as we know it. Quarks are the building blocks of protons and neutrons, while gluons are the particles that bind quarks together through the strong nuclear force. In initial tests at Brookhaven and similar facilities around the world, this quark-gluon plasma has shown a crucial property that connects directly to our understanding of the early universe. It displays extremely low viscosity or resistance to flow. Scientists call it a nearly perfect liquid, meaning it flows with almost no friction. To grasp the profound importance of this discovery, we must return to those primordial energy fields that inflationary theory says spawned the Big Bang. The thinking is that those fields, despite being incredibly smooth on average, contained tiny quantum fluctuations, random variations at the smallest scales allowed by physics. During inflation, these microscopic fluctuations were blown up to enormous size, stretched across vast cosmic distances, asterisk in the ultra-dense quark-gluon mix that filled the early universe. These fluctuations generated pressure waves, or ripples, much like sound waves moving through a medium. Because the quark-gluon plasma was such a perfect liquid with very low viscosity, these waves could propagate efficiently without being dampened out. As the universe evolved and expanded, cooling from its initial inferno, these ripples became frozen into the fabric of space itself. They gave rise to variations in the density of matter, with some regions slightly denser than average and others slightly less dense. Over billions of years, gravity would amplify these small differences, pulling matter into the denser regions and creating the cosmic web of structure we observe today. Asterisk, amazingly, the imprint of those primordial ripples, originating in the first fraction of a second after the Big Bang, is still out there today. It exists in a faint signal that was discovered accidentally back in the 1960s, during an era when scientists were developing sensitive radio receivers for telecommunications. Working for the Bell Telephone Company, physicists Arno Penzias and Robert Wilson had built a giant horn-shaped antenna in New Jersey, intended for satellite communications. But wherever they pointed this sensitive instrument across the sky, the device picked up persistent, excessive noise in the microwave portion of the electromagnetic spectrum. They initially suspected interference from urban areas, atmospheric effects, or even droppings from pigeons nesting in the antenna, which they painstakingly cleaned out. Asterisk, that noise turned out to match a theoretical prediction that had been made years earlier by physicist George Gamow and his colleagues, that in the wake of the Big Bang, the universe was filled with an incredibly hot, dense cloud of plasma that scattered all light like a thick fog. Photons couldn't travel far before colliding with charged particles, so the universe was opaque to electromagnetic radiation. As the universe expanded and cooled over hundreds of thousands of years, the temperature eventually dropped to about 3,000 degrees, cool enough for electrons to combine with atomic nuclei to form neutral atoms. At this point, light could suddenly travel freely through space. The universe became transparent in a cosmic transition called recombination, asterisk. As the universe continued expanding and cooling after this moment of first light, the spectral signature of this primordial radiation shifted. The expansion of space stretched the wavelengths of these photons, shifting them from visible light through infrared and eventually into the microwave range. This is what Penzias and Wilson detected with their antenna, the cooled, stretched echo of the Big Bang itself, now called the cosmic microwave background radiation. For this momentous discovery, they were awarded the Nobel Prize in Physics. The smooth contours of a microwave light they recorded showed that the early universe was remarkably uniform. The same temperature, too, within a few parts in 100,000 in all directions. Asterisk, however. Scientists realized that they would need to look much closer and with greater precision to find the subtle imprint of cosmic inflation, the tiny variations that would eventually grow into galaxies and larger structures. The Space Shuttle Discovery lifted the Hubble Space Telescope into orbit on April 24th, 1990, in one of the most important scientific milestones of our time. This remarkable observatory has revolutionized astronomy, providing incredibly sharp images of the cosmos from above Earth's distorting atmosphere. But another launch, arguably just as important for cosmology, took place 5 months earlier, November 1989. The Cosmic Background Explorer, COBE for short, was sent into orbit to take a much harder and more detailed look at the microwave radiation discovered by Penzias and Wilson. Asterisk, the groundbreaking results from COBE came out 2.5 years later, in 1992, and they stunned the scientific community. The light of the early universe, mapped across the entire sky with unprecedented precision, contained a subtle pattern of slightly hotter and slightly cooler spots. Temperature variations of only a few millionths of a degree in this cosmic baby. Picture, scientists could see nothing less than the seeds of everything around us today. The pattern was smooth on the largest scales, confirming the basic predictions of inflation, but it also showed significant clumps and variations at smaller scales. These are the regions from which gravity would eventually gather matter to form vast clouds of gas. Then the first stars, and ultimately the galaxies and galactic clusters that fill the universe today. Asterisk with this cosmic template in hand, revealing the initial conditions of the universe. Astronomers set out to discover how the patterns and dimensions of cosmic structure evolved over billions of years of time. They wanted to map the distribution of galaxies and see if it matched what would be expected from those early seeds. In an age of computer-controlled telescopes and automated observing systems, astronomers could now launch huge international collaborations with the ambitious goal of mapping a large fraction of the visible universe in 3 dimensions, recording not just the positions of galaxies on the sky, but also their distances from Earth. Asterisk at Apache Point Observatory in New Mexico. The Sloan Digital Sky Survey set the standard for mass production astronomy on an industrial scale. The project uses specially designed steel plates drilled with hundreds of holes that exactly match the positions of galaxies in specific regions of the night sky. After carefully plugging fiber optic sensors into these holes, each aligned with a particular galaxy, the plates capture the light from hundreds of distant galaxies simultaneously during a single night of observing. From the spectrum of that light, analyzing how it has been stretched by cosmic expansion, astronomers can calculate the distances of these galaxies from Earth with remarkable precision. Over years of observation, this survey has mapped millions of galaxies across vast swaths of the universe. Asterisk, another ambitious survey is named the 2-Micron All-Sky Survey, or 2MASS, named after the frequency of infrared light that its specialized detectors are precisely to capture. Infrared light can penetrate cosmic dust that blocks visible light, revealing galaxies and structures that would otherwise remain hidden. In detailed maps created from 2MASS data, we can examine a region about 60 million light-years across. A relatively local cosmic neighborhood, the local group of galaxies, including our own Milky Way along with the Andromeda Galaxy and dozens of smaller satellite galaxies, sits near the center of this view. This is our immediate intergalactic neighborhood, the cluster of galaxies gravitationally bound to our own. When we jump farther out to examine a region about 200 million light-years across, we can see our location in a broader context. We're connected to the densely packed Virgo supercluster, the nearest large concentration of galaxy clusters, which serves as our intergalactic city. The gravitational pull of this massive structure influences the motion of our galaxy and our neighboring galaxies. Stepping out even farther to a region spanning more than 320 million light-years across, we begin to see the full breadth of our local region of the universe and its remarkable structure. Galaxies line up in vast walls and graceful arcs like cosmic highways stretching across space. Beyond and between these concentrations of galaxies are sparsely populated voids, enormous regions containing very few galaxies, like rural cosmic countryside separating the great cities of galaxies. Asterisk. Moving outward with the accumulated data from these surveys, we can examine a region more than 650 million light-years across, then almost 2 billion light-years, then 3.2 billion light-years across. Finally, we can map a region 6.5 billion light-years from end to end, representing a significant fraction of the observable universe. This represents the cosmic continent, revealing the large-scale structure of the universe in all its complexity. In the very middle of these vast maps, positioned at our observational vantage point, sits our Milky Way galaxy. This galaxy, so immense from our earthly perspective with its hundreds of billions of stars, appears in these maps as less than a single speck, almost invisible against the vastness of cosmic structure. Asterisk, the two-mass study, the Sloan Digital Sky Survey, and the 2-degree field galaxy redshift survey conducted in Australia have collectively extended our three-dimensional maps of the universe to encompass regions about a quarter of the way back to the beginning of time, back to the Big Bang itself. Together, these monumental efforts have laid out a grand cosmic roadmap, charting the distribution of matter across billions of light-years. The patterns they reveal, the walls, filaments, clusters, and voids, represent the mature form of structure that began with tiny quantum fluctuations in the first moments of the universe. Asterisk, COBE's successor mission, the Wilkinson Microwave Anisotropy Probe, or WMP, was launched in 2001 to scan the early universe with even greater precision for the fine-scale origins of this cosmic atlas. WMP traveled far beyond any interference from Earth's atmosphere or radiation, journeying to a special position in space called the L2 Lagrange point, gravitationally balanced between the Earth and the Sun, roughly 1 million miles from our planet. There, for 9 years of operation, far exceeding its original mission plan, the spacecraft's sensitive detectors took in the pristine light of deep space, measuring the cosmic microwave background radiation with exquisite detail. Asterisk, this is what WMAP revealed: a pattern remarkably consistent with the filaments, walls, clusters, and voids that had evolved in the universe at large over billions of years. The statistical properties of the hot and cold spots in the cosmic microwave background matched predictions based on the observed large-scale structure, providing powerful confirmation that we understand the basic processes that shape the cosmos. Scientists have been poring over the WMP data and data from its successor, the Planck satellite launched in 2009, searching for clues to the true dimensions of the universe beyond what we can directly observe. Asterisk, one group of researchers, for example, carefully looked for repeating patterns in the microwave background that could be evidence of acoustic oscillations, pressure waves that ricocheted back and forth through the hot plasma of the early universe before recombination. These waves would have had a characteristic size scale, like the wavelength of a sound wave, determined by how far they could travel in the time available. If the universe were relatively small, one might see the same pattern repeated multiple times across the sky, like a wallpaper pattern. The scientists saw no such repetitions, which implies that the universe had grown so enormously large during the inflationary period that such waves could not cross the entire universe. even traveling at the speed of light. The universe is bigger than the distance light could have traveled in the time available. Asterisk. The researchers then performed detailed mathematical calculations based on this observation and other features of the microwave background data. They reported that the entire universe, far beyond what we can observe, must have a minimum diameter of at least 78 billion light years. Some analyses suggest it could be vastly larger still, perhaps hundreds of billions or even trillions of light years across. So, what is the maximum possible size of the universe, and what could lie beyond our cosmic horizon? These questions probe the very limits of scientific inquiry. We will never know for sure what lies beyond our visual horizon. That boundary defined by the finite speed of light and the finite age of the universe. Light from regions beyond this horizon simply hasn't had time to reach us yet, and never will if the universe continues accelerating. However, astronomers and physicists are turning up surprising hints about the nature of the cosmos, even in the universe we can observe. Hints that reshape our understanding of reality itself. Asterisk to ancient observers. The universe was composed of 5 classical elements. Earth, representing solid matter. Water, representing liquids. Air, representing gases. Fire, representing energy and transformation. And a 5th element called quintessence, representing space itself. The Greek philosopher Aristotle believed the stars, seemingly unchanging and incorruptible compared to the earth, were made of this special 5th element. Today, modern science is finding that space, in fact, does have a character and properties of its own that Aristotle could never have imagined. Space is not merely an empty stage on which matter and energy perform, but rather an active participant in cosmic evolution. Asterisk astronomers have made careful calculations of the gravitational pull needed to bind stars together as they orbit within a galaxy, or galaxies as they orbit around each other within a cluster of galaxies. By measuring the speeds at which stars and galaxies move, they can infer how much mass must be present to provide the gravitational force required to hold these structures together. Time and again, across cosmic scales, they have found that there is simply nowhere near enough visible matter stars, gas, dust, and all forms of matter that emit or absorb light to account for the observed gravitational effects. Something else, something invisible, must be providing most of the gravitational pull. Asterisk the missing ingredient. Its precise identity still unknown despite decades of intensive search. Astronomers call dark matter. This mysterious substance doesn't emit, absorb, or reflect light, making it invisible to all forms of electromagnetic radiation. We know it exists only through its gravitational influence on visible matter. Current estimates suggest that dark matter outweighs ordinary matter by a factor of about 5 to 1. In supercomputer simulations of cosmic evolution that attempt to recreate the formation of galaxies and large-scale structure, dark matter must be added into the calculations to supply the gravitational tug needed to form the observed web pattern of filaments in walls, voids, and dense clusters we see in the universe at large. Without dark matter, the simulations produce a universe that looks nothing like our own. Asterisk, but something else. Something even stranger appears to be happening on the largest cosmic scales affecting the evolution of the universe as a whole. Astronomers have been making refined measurements of the cosmic expansion rate using a new type of astronomical distance marker, seeking to understand how the expansion has changed over cosmic history. They wanted to know whether gravity pulling backward on the expansion was gradually slowing down the pace at which the universe is growing, as had long been assumed. Perhaps the universe would eventually stop expanding and collapse back on itself in a big crunch. Or perhaps it would expand forever, but at an ever-decreasing rate. Asterisk, the distance markers these astronomers used are called Type Ia supernova. Spectacular. Stellar explosions that are thought to burn at remarkably uniform peak intensities throughout the universe. These cosmic lighthouses all reach approximately the same intrinsic brightness at maximum, making them excellent standard candles for measuring distances. by measuring changes in the apparent brightness of these supernova at various distances observing explosions that occurred at different times in cosmic history. Researchers can detect changes in the cosmic expansion rate over billions of years. They can test whether the universe has been expanding at a steady rate, slowing down, or speeding up. Asterisk, to the complete surprise of the astronomical community, the data collected by two independent teams in the late 1990s showed something completely unexpected. The universe as a whole is not only expanding, but it's actually accelerating outward. Distant supernova appeared dimmer than expected, indicating they're farther away than they should be if the universe were expanding at a constant rate or slowing down. Something is pushing space apart with increasing vigor, overwhelming the attractive pull of gravity. This discovery was so surprising and significant that it earned the Nobel Prize in Physics in 2011 for the leaders of the teams that made it. The culprit driving this acceleration is thought to be a form of energy welling up from the vacuum of space itself, similar in some ways to the energy that drove cosmic inflation in the early universe, but much weaker in intensity. By emerging in minute quantities everywhere throughout space, this mysterious energy is steadily pushing space outward across the whole universe. Over cosmic time, as the universe has expanded and the density of matter has decreased, this so-called dark energy has grown in relative importance. It has become an astonishing 3/4 of all the mass and energy in the universe, with dark matter accounting for most of the rest in ordinary matter. Everything we can see making up less than 5% of the cosmic inventory. Asterisk, with observational data like this pointing to underlying dynamics and hidden components within our universe. Some scientists and theorists are beginning to think about the cosmos in far broader terms than ever before, contemplating possibilities that would have seemed like pure fantasy just decades ago. There is a version of inflationary theory, for example, developed by physicists like Andre Lind and others, that suggests we may live in just one of countless universes, a vast multiverse where separate cosmic domains coexist. In this model, often called eternal inflation, the inflationary process that created our universe never truly ends. While inflation stopped in our cosmic patch, allowing matter and energy to condense and evolve into stars and galaxies, it continues. In other regions, constantly spawning new universes. Asterisk, these hypothetical other universes may exist side by side with our own but remain forever separate, unable to interact or communicate with one another in any way. Like bubbles continuously rising and expanding in a cosmic ocean of inflating space, they are born, grow, and evolve across the infinite reaches of reality. Each bubble universe might have different physical properties, different values for the fundamental constants of nature, different numbers of dimensions, or different laws of physics entirely. Some might be hospitable to life and complexity, while others might be sterile and simple. We happen to find ourselves in one that allows for stars, planets, chemistry, and ultimately conscious observers. Perhaps inevitably so, given the anthropic requirement that we can only exist in a universe capable of producing us. Asterisk just 500 years ago. In Galileo's time during the early 17th century, many people looked out into the night sky and saw a universe of lights that they believed was centered on the Earth, with the sun, moon, planets, and stars all revolving around our world. As the focus of creation, the invention and improvement of the telescope by Galileo and his contemporaries began to reveal a very different reality. It showed stars far more numerous and distant from our planet than anyone had imagined, scattered throughout vast depths of space. Later, observations revealed entire galaxies beyond our Milky Way, then clusters of galaxies, superclusters, and beyond them the vast walls and filaments of matter that constitute the large-scale structure of the observable universe. Asterisk, the newer theoretical ideas about the possible size and nature of the universe, cosmic inflation. The multiverse, universes beyond our horizon amount to a quantum leap in our sense of cosmic scale. extending the realm of existence far, far beyond what we can observe even with our most powerful instruments. These ideas suggest that the 92 billion light-year span of the observable universe is just the tiniest fragment of a vastly larger cosmos, or perhaps just one universe among an infinite number. Some physicists and philosophers have asked whether these discoveries about cosmic immensity push us, on our tiny out-of-the-way planet orbiting an ordinary star in the outer regions of a typical galaxy, into a smaller and smaller corner of creation, rendering us insignificant. Asterisk, yet there's another perspective to consider. Does our ability as conscious beings to comprehend and imagine the far limits of time and space, to unravel the mathematical laws governing cosmic evolution, to peer back to the first moments of the Big Bang, somehow expand our importance in the grand scheme of things? We are, after all, the universe becoming aware of itself, matter and energy organized to such a way as to ponder its own existence and origins. In this sense, we occupy a central position not in physical space, but in the realm of meaning and understanding. We are small in size, but vast in comprehension, tiny in extent, but infinite in curiosity and wonder. Asterisk, the journey from ancient sky watchers to modern cosmologists represents one of humanity's greatest intellectual achievements, a testament to the power of observation, reason, and imagination. We have measured the cosmos with extraordinary precision, traced its evolution across billions of years, and glimpsed possibilities that extend far beyond what any previous generation could have conceived. Each discovery reveals new mysteries, new questions to investigate, new frontiers to explore. The universe, whether it encompasses just our observable cosmic bubble or extends infinitely in a vast multiverse, continues to inspire awe and wonder, driving us to look deeper, reach farther, and understand more completely the magnificent reality in which we find ourselves. Asterisk. The quest to understand the full scope of the universe has led scientists down unexpected pathways, revealing connections between the largest structures in the cosmos and the smallest constituents of matter. This interplay between the macroscopic and the microscopic represents one of the most profound insights of modern physics. The rules governing subatomic particles in quantum mechanics appear to have shaped the entire universe during its inflationary birth, while the overall geometry and fate of the cosmos depends on the precise properties of fundamental particles and forces. When we examine the cosmic microwave background radiation in even greater detail, we find patterns that encode information about the fundamental physics of the early universe. The size of the hot and cold spots in this ancient light, for instance, tells us about the density of matter at the moment of recombination when the universe became transparent. The spectrum of sizes in these fluctuations reveals information about the relative amounts of ordinary matter, dark matter, and dark energy. Scientists can measure these patterns with extraordinary precision and compare them to theoretical predictions, testing our understanding of physics at energy scales far beyond what any particle accelerator can achieve. Asterisk, the European Space Agency's Planck satellite, which operated from 2009 to 2013, pushed these measurements to new levels of accuracy. Its detectors cooled to just 1/10 of a degree above absolute zero to minimize interference from thermal noise, mapped the cosmic microwave background across the entire sky with unprecedented resolution and sensitivity. The data from Planck has allowed cosmologists to determine the age of the universe to within a few tens of millions of years, to measure the cosmic expansion rate with percent-level precision, and to constrain the properties of dark matter and dark energy with remarkable accuracy. Asterisk, one of the most intriguing findings from these precise measurements concerns the geometry of space itself. Einstein's general theory of relativity tells us that space can curve in response to the presence of matter and energy, much like a rubber sheet bends when you place a heavy ball on it. On cosmic scales, this curvature determines the overall geometry of the universe. Space could curve back on itself like the surface of a sphere, making the universe finite in extent, though without any edge or boundary. Alternatively, space could curve in the opposite direction like a saddle, making the universe infinite and open. Or space could be perfectly flat, with the angles of triangles always adding up to exactly 180 degrees, also allowing for an infinite universe. Asterisk, the measurements of the cosmic microwave background tell us that, to within measurement. Precision, the universe appears to be almost perfectly flat on the largest observable scales. This flatness is itself a prediction of inflationary theory. During the exponential expansion of inflation, any initial curvature would have been stretched out and smoothed away, much like the surface of a balloon appears flatter and flatter as it inflates to larger and larger sizes. The observed near-perfect flatness provides strong support for the inflationary scenario and suggests that the total universe is vastly larger than what we can observe. If there is any curvature at all, it must be on scales far exceeding the observable universe. Asterisk, this flatness also has implications for the fate of the universe. A flat or nearly flat universe with the observed amount of dark energy will continue, expanding forever with the expansion rate accelerating over time. Galaxies beyond our local gravitationally bound group will recede from us ever faster, eventually moving away so rapidly that light from them can no longer reach us. The observable universe will paradoxically shrink even as the universe itself grows larger. In the distant future, hundreds of billions of years from now, intelligent observers in our galaxy would see a much lonelier cosmos, with nearly all other galaxies having disappeared beyond the horizon of observation, their light redshifted beyond detectability. This future cosmic loneliness raises interesting questions about how fortunate we are to live in the current epoch of cosmic history. We exist at a time when the universe is old enough to have formed stars, planets, and complex chemistry necessary for life, yet young enough that we can still observe the cosmic microwave background in distant galaxies that reveal the universe's history and structure. A civilization arising just a few 100 billion years in the future might find itself unable to discover many of the fundamental truths about cosmology that we have been able to uncover, simply because the relevant evidence would have receded beyond reach. Asterisk, the role of dark matter in cosmic evolution remains one of the most pressing mysteries in modern physics. While we know with great confidence that dark matter exists based on its gravitational effects, we still don't know what it's made of. Scientists have proposed numerous candidates for dark matter particles, each with different properties and implications. One popular class of candidates are called dual UIMPs, or weakly interacting massive particles. These hypothetical particles would interact with ordinary matter only through gravity and possibly through the weak nuclear force, making them extraordinarily difficult to detect directly. Asterisk experiments deep underground in locations around the world are searching for the rare events that might occur when a dark matter particle collides with an atomic nucleus in a sensitive detector. These experiments must be conducted deep underground to shield them from cosmic rays and other background radiation that could mimic or mask a potential dark matter signal. Detectors filled with ultra-pure materials are cooled to extremely low temperatures and monitored for tiny flashes of light or small amounts of heat that might indicate a dark matter interaction. Despite decades of searching with increasingly sensitive instruments, these direct detection experiments have not yet produced a confirmed discovery of dark matter particles, though they have ruled out many possible models and narrowed the search. Asterisk other. Experiments are searching for dark matter indirectly by looking for the products of dark matter particle annihilation or decay in space. If dark matter particles occasionally collide and annihilate each other, they might produce gamma rays, neutrinos, or other particles that we could detect. Space-based telescopes and ground-based observatories scan the sky for unusual signatures that might reveal the presence of dark matter. The center of our galaxy, where dark matter is expected to be particularly concentrated, is a prime target for these searches. Asterisk particle accelerators like the Large Hadron Collider at CERN in Switzerland are also searching for dark matter by attempting to create it in high-energy collisions between protons. If dark matter particles exist and can be produced at accessible energies, they might be created in these collisions and then stream away from the collision point without interacting with the detector. Physicists look for events where energy appears to be missing, potentially carried away by invisible dark matter particles. These complementary approaches, direct detection, indirect detection, and collider production together form a comprehensive strategy to identify the nature of dark matter. Asterisk. Some scientists have proposed more exotic alternatives to conventional dark matter particles. Modified theories of gravity suggest that perhaps the gravitational effects we attribute to dark matter are actually evidence that our understanding of gravity needs revision on galactic scales. While Einstein's general relativity has passed, every test in our solar system and in other strong field environments like binary pulsars and merging black holes, perhaps it breaks down on the scales of galaxies and galaxy clusters. Various modified gravity theories have been proposed, such as modified Newtonian dynamics or MOND, which changes the inverse square law of gravity at very low accelerations. Asterisk, however, these modified gravity theories face significant challenges in explaining all the observations. While some can account for the rotation curves of galaxies, they struggle to explain the behavior of galaxy clusters, the patterns in the cosmic microwave background, and the distribution of matter on the largest scales. The most compelling evidence for dark matter as actual particles rather than modified gravity comes from observations of colliding galaxy clusters, such as the famous bullet cluster. In these collisions, the hot gas in the clusters interacts and slows down the gravitational mass, as measured by gravitational lengthening of background galaxies, passes through largely unaffected. This separation between the location of the visible matter and the location of the gravitational mass provides strong evidence for dark matter as a distinct substance. Asterisk, dark energy. The mysterious force accelerating the expansion of the universe presents an even deeper puzzle than dark matter. At least with dark matter, we have a basic conceptual framework, some new type of particle that doesn't interact electromagnetically. With dark energy, we're confronted with something that seems to challenge our fundamental understanding of space, time, and quantum mechanics. The simplest explanation for dark energy is that it represents the energy of empty space itself. What physicists call vacuum energy or the cosmological constant, the same term Einstein introduced and later abandoned. Asterisk, quantum field theory predicts that empty space should indeed have energy due to quantum fluctuations, with virtual particles constantly popping in and out of existence. However, when physicists calculate what this vacuum energy should be based on quantum field theory, they get an answer that is larger than the observed dark energy density by a factor of about 10 to the power of 120. This represents perhaps the worst prediction in the history of physics. A discrepancy so enormous that it's called the cosmological constant problem. Why the actual vacuum energy is so much smaller than theoretical expectations remains completely unexplained. Asterisk. Some physicists have proposed that dark energy might not be a constant property of space, but rather a dynamic field that changes over time, called quintessence after Aristotle's fifth element. In these models, the dark energy density could vary as the universe evolves, potentially increasing or decreasing with time. If dark energy is increasing, the accelerated expansion could eventually become so rapid that it tears apart galaxies, stars, planets, and eventually atoms themselves in a scenario called a Big Rip. If dark energy is decreasing, or could even become negative, the universe might eventually stop accelerating and could potentially recollapse. Current observations are consistent with a constant dark energy density, but they don't rule out slow changes over cosmic time. Asterisk, another approach to understanding dark energy involves questioning whether general relativity correctly describes gravity on cosmological scales. Just as some scientists propose modified gravity to explain dark matter, others suggest that modifications to general relativity on the largest scales might explain the accelerated expansion without requiring dark energy. These theories face the challenge of modifying gravity in just the right way to explain cosmic acceleration, while still agreeing with all the other successful predictions of general relativity, from the precession of Mercury's orbit to gravitational waves from merging black holes. The discovery of gravitational waves has opened an entirely new window on the universe, allowing us to observe phenomena that are invisible to electromagnetic radiation. In September 2015, the LIGO observatories detected gravitational waves from two merging black holes more than 1 billion light-years away, confirming a century-old prediction of Einstein's general relativity. These ripples in space-time, itself traveling at the speed of light, caused the 4-kilometer arms of the LIGO detectors to change in length by less than the width of a proton. Since that first detection, dozens of additional gravitational wave events have been observed, including mergers of black holes, neutron stars, and Nix systems. Gravitational wave astronomy offers unique opportunities to probe the universe in ways that complement electromagnetic observations. Gravitational waves can travel through matter and energy that would block light, allowing us to observe phenomena deep inside dense stellar cores or in the immediate vicinity of black holes. They carry information about the strong gravitational fields and highly dynamic spacetime geometry during violent cosmic events, testing general relativity and extreme conditions. Future space-based gravitational wave detectors like LISA, the Laser Interferometer Space Antenna, will be able to detect waves from supermassive black hole mergers, stellar mass objects falling into supermassive black holes, and, potentially, even gravitational wave signatures from the inflationary epoch itself. If inflationary gravitational waves could be detected, they would provide a remarkable window into the very first moments of the universe, before even a trillionth of a second had elapsed. These primordial gravitational waves would have been produced by quantum fluctuations during inflation, just like the density fluctuations that seeded cosmic structure. They would have left a distinctive imprint on the polarization pattern of the cosmic microwave background radiation, a swirling pattern called beam mode polarization. Several experiments are racing to detect this signature, operating from remote locations like the South Pole, where atmospheric interference is minimal. The detection of primordial gravitational waves would not only confirm the inflationary scenario, but would also probe physics at energy scales approaching the Planck scale, where quantum mechanics and gravity become equally important. This is a realm of quantum gravity where our current theories break down and a more fundamental theory is needed. String theory, loop quantum gravity, and other approaches to quantum gravity attempt to describe physics at these extreme energies. But we currently have no experimental tests of these ideas. Inflationary gravitational waves could provide our first observational glimpse into this otherwise inaccessible frontier of physics. The study of the early universe also connects to questions about the origin of matter itself. One of the great mysteries of cosmology is why the universe contains matter at all rather than being filled with pure energy or radiation. According to our understanding of particle physics, the Big Bang should have created equal amounts of matter and antimatter. When matter and antimatter meet, they annihilate each other and convert into pure energy in the form of photons. If matter and antimatter had been produced in exactly equal quantities, they should have completely annihilated, leaving a universe filled with light but no atoms, no stars, no planets, and no asterisk, yet the universe clearly contains a great deal of matter and virtually no antimatter. Somewhere in the first fractions of a second after the Big Bang, a tiny asymmetry must have been created, producing slightly more matter than antimatter. When the matter and antimatter annihilated, a small residue of matter remained, perhaps one extra matter particle for every 10 billion matter-antimatter pairs. This leftover matter is what makes up everything we see in the universe today. Understanding how this matter-antimatter asymmetry arose is one of the fundamental questions in physics, touching on the deepest properties of particles and forces. Several mechanisms have been proposed to generate this asymmetry, generally requiring physics beyond the standard model of particle physics. The conditions necessary for creating more matter than antimatter, worked out by physicist Andrei Sakharov, include violation of certain symmetries that the standard model only barely allows. Experiments at particle accelerators and with neutrinos are searching for evidence of these symmetry violations and attempting to determine whether they are large enough to explain the observed matter dominance. The answer may lie in the properties of exotic particles that existed only in the extreme conditions of the very early universe, or in subtle differences between the behavior of matter and antimatter that we haven't yet discovered. Asterisk the possibility that our universe is just one bubble in a vast multiverse raises profound questions about the nature of physical laws and whether they could have been different. In the multiverse scenario suggested by eternal inflation, different bubble universes could have different values for the fundamental constants of nature, the strength of gravity, the mass of the electron, the speed of light, and so on. Some combinations of these constants would allow for complex structures, stars, planets, and potentially life, while other combinations would produce sterile universes, containing only simple particles or nothing but black holes. Asterisk, this has led some physicists to invoke the anthropic principle as an explanation for why we observe the particular values of constants that we do. We necessarily find ourselves in a universe capable of supporting our existence, even if such universes are rare in the larger multiverse. While this reasoning is logically sound, many scientists find it unsatisfying, as in preferring to search for more fundamental reasons why the constants have their observed values. The debate continues about whether anthropic reasoning represents a legitimate scientific principle or a retreat from the goal of finding deeper explanatory theories. Asterisk. The concept of the multiverse itself raises questions about what constitutes science. If other universes are forever beyond our ability to observe or interact with them, can theories about the multiverse be tested and falsified? Some philosophers of science argue that multiverse theories violate the requirement that scientific theories make testable predictions. Others counter that if a theory like eternal inflation makes successful predictions about our own universe and happens to also predict the existence of other universes as an unavoidable consequence, then the multiverse aspect comes along as a prediction of an otherwise testable theory. Asterisk, one approach to testing multiverse theories is to look for potential collisions between bubble universes. If our cosmic bubble collided with another bubble universe in the distant past, it might have left a distinctive imprint in the cosmic microwave background, a circular pattern marking the collision zone. Several groups have searched the microwave background data for such signatures without finding convincing evidence, though this doesn't rule out the multiverse, since collisions might simply not have occurred within our observable region or might have happened too early to leave a detectable mark. Asterisk. Another testable aspect of some multiverse models involves subtle statistical features in the distribution of galaxies or the properties of the cosmic microwave background that could reveal whether we live in a typical bubble universe or an unusual one. If we could determine that certain features of our universe are statistically unlikely given a particular multiverse model, it might allow us to rule out that model or refine our understanding of how different bubble universes are distributed. Asterisk. The tools and techniques that astronomers use to study the universe continue to advance at a remarkable pace. The James Webb Space Telescope, launched in December 2021, represents the next generation of space observatories. With its large segmented mirror and infrared detectors cooled to near absolute zero, Webb can peer deeper into space and further back in time than ever before. It has already captured images of galaxies as they appeared less than 500 million years after the Big Bang, revealing an unexpected abundance of bright, massive galaxies in the early universe that challenges our models of galaxy formation. Asterisk. Ground-based telescopes are also growing more powerful. The next generation of extremely large telescopes, with primary mirrors 30 meters or more in diameter, are under construction in Chile and Hawaii. These instruments will collect more light than any previous optical telescope, allowing them to study the faintest and most distant objects in exquisite detail. equipped with adaptive optic systems that compensate for the blurring effects of Earth's atmosphere. They will achieve resolution rivaling that of space telescopes while benefiting from the much larger collecting area possible with ground-based instruments. Radio astronomy arrays, connecting telescopes across continents or even around the globe, can achieve angular resolution far exceeding any single telescope. The Event Horizon Telescope collaboration, linking radio dishes around the world, has produced images of the supermassive black holes at the centers of the Milky Way and the nearby galaxy M87. These images show the shadow of the black hole against the glowing gas swirling around it, providing direct visual confirmation of these extreme objects predicted by general relativity. Future expansions of these networks will enable even sharper images in movies, showing how matter behaves in the most extreme gravitational fields in the universe. Neutrino astronomy represents another new frontier in observing the cosmos. Neutrinos are ghostly particles that barely interact with matter, allowing them to escape from environments too dense for light to penetrate. The IceCube Neutrino Observatory, built into a cubic kilometer of ice at the South Pole, detects high-energy neutrinos from cosmic sources by looking for the flashes of light produced when rare neutrino interactions occur in the ice. These neutrinos can point back to violent events like supernova explosions, the cores of active galaxies, or other exotic phenomena, providing information inaccessible to conventional telescopes. Multi-messenger astronomy, combining observations of light, gravitational waves, neutrinos, and potentially even cosmic rays from the same event, is revealing cosmic phenomena in unprecedented detail. When two neutron stars merged in August 2017, the event was detected both in gravitational waves by LIGO and in gamma rays by orbiting telescopes. Within hours, observatories around the world and in space were trained on the source, capturing the optical, infrared, ultraviolet, and X-ray light from the explosion. This bonanza of data revealed that neutron star mergers are sites where heavy elements like gold and platinum are forged, solving a long-standing mystery about the origin of these elements. As we look to the future of cosmic exploration, new questions continually emerge. What is the nature of the singularities hidden inside black holes where our current theories break down? Are there observable consequences of quantum gravity that we could detect? Could the universe have had a pre-Big Bang history, with our current expansion phase emerging from a previous contracting phase in a cyclic model? Is dark matter composed of a single type of, or a whole dark sector of particles with its own forces and interactions? Could dark energy be evolving in ways that will become measurable as our observations improve? The question of whether life exists elsewhere in the universe has moved from philosophy to observational science. The discovery of thousands of planets orbiting other stars has revealed that planetary systems are common, and many of these planets orbit in their star's habitable zone where liquid water could exist on the surface. The James Webb Space Telescope and future missions are beginning to analyze the atmospheres of these distant worlds, searching for chemical signatures that might indicate biological activity. Within our own solar system, moons like Europa orbiting Jupiter and Enceladus orbiting Saturn show evidence of liquid water oceans beneath their icy surfaces, making them potential habitats for life. If life is common in the universe, it raises the question of whether intelligent, technologically advanced civilizations might exist on other worlds. The search for extraterrestrial intelligence, or SETI, scans the sky for artificial signals that might indicate the presence of alien technology. So far, these searches have found nothing convincing, leading to what's called the Fermi paradox. If intelligent life is common, where is everybody? Various solutions have been proposed, from the idea that technological civilizations inevitably self-destruct to the possibility that we're among the first intelligent species to arise in our galaxy. Each answer carries profound implications. For humanity's future, The study of the universe ultimately raises deep philosophical and existential questions. What does it mean that we live in a possibly infinite universe, or one of countless universes in a vast multiverse? How should we think about our place in a cosmos so much larger and older than ourselves? Does the apparent fine-tuning of physical constants necessary for our existence demand explanation, or is it simply how things are? These questions sit at the intersection of science, philosophy, and theology, areas where empirical investigation, logical reasoning, and human values all play important roles. Asterisk throughout history, revolutions in our understanding of the cosmos have often prompted reevaluations of humanity's place in nature. Copernicus removed Earth from the center of the solar system. Hubble revealed our galaxy as one among billions. Now we contemplate our observable universe as perhaps a tiny bubble in an infinite cosmos. Each step might seem to diminish our significance, yet each also represents a triumph of human reason and creativity. We have used mathematics, observation, and ingenuity to comprehend realms far beyond our direct experience, from the quantum realm to the cosmic horizon. Asterisk. The tools of science have proven extraordinarily powerful for uncovering the workings of nature, but they have limitations. Science deals with testable hypotheses, reproducible experiments, and predictions that can be verified or falsified through observation. Questions about ultimate purpose, meaning, or value lie outside this framework, though they remain deeply important to human existence. Science can tell us how the universe began and evolved, but it cannot tell us why there is something rather than nothing, or what we should do with our knowledge. Asterisk, the universe revealed by modern science is both humbling and exhilarating. It is humbling to recognize how small we are in space and time, how recent our appearance in cosmic history, how fragile our existence on this pale blue suspended in a sunbeam. As Carl Sagan memorably described Earth, yet it is exhilarating too. Realize that this tiny, fragile species has managed to decode the history of the cosmos, to trace the evolution of matter and energy across billions of years, to glimpse the quantum fluctuations that seeded galaxies and ultimately led to our own existence. Asterisk, we are, in a sense, the universe contemplating itself. Matter organized in such intricate ways that it can ponder its own origins and nature. The atoms in our bodies were forged in the cores of stars or in supernova explosions, scattered through space and eventually incorporated into planets and living beings. We are literally made of star stuff, connected through cosmic history to the most distant reaches of space and time. This connection implies a profound relationship between mind and cosmos, between conscious observers and the universe they observe and seek to understand. Asterisk, looking forward, we can anticipate continued discoveries that will reshape our understanding of the universe and our place within it. Perhaps we will finally identify dark matter and dark energy, solving two of the deepest mysteries in physics. Perhaps we will detect primordial gravitational waves and peer back to the inflationary epoch, testing our ideas about cosmic origins. Perhaps we will find evidence of life beyond Earth, ending cosmic loneliness and revealing whether biology is a universal phenomenon. Perhaps we will develop a theory of quantum gravity that unifies our understanding of nature at all scales. Asterisk, whatever discoveries await. The quest to understand the universe represents one of humanity's noblest endeavors. It requires the best of human qualities: curiosity, creativity, patience, rigor, and the courage to question cherished beliefs when evidence demands it. It brings together people from all nations and backgrounds in a common enterprise transcending political, cultural, and ideological boundaries. It produces knowledge that belongs to all humanity, expanding our collective understanding and opening possibilities we can barely imagine. The question of how large the universe is has led us on an extraordinary intellectual journey, from ancient philosophers counting the heavens to modern cosmologists mapping dark energy across billions of light years. The answer has expanded far beyond what anyone could have imagined just a century ago. We now know that our observable universe spans 92 billion light years, that the total universe likely extends vastly beyond this horizon, and that our cosmos may be just one bubble in an infinite multiverse. Asterisk, yet, for all this knowledge, mysteries remain. We still don't know what dark matter and dark energy really are, whether the universe is truly infinite, what if anything exists beyond our cosmic horizon, or why the laws of physics take the form they do. These unanswered questions ensure that the adventure of cosmic discovery will continue, that future generations will inherit not a completed encyclopedia of knowledge, but an ongoing quest to push back the boundaries of ignorance and expand the frontiers of understanding. In this quest, each answer reveals new questions. Each discovery opens new mysteries, and the universe continues to surprise and inspire us with its grandeur, complexity, and the deep questions it poses about existence itself.